Today's learning goal is to apply Newton's reformulation of Kepler's third law. Apply Newton's reformulation of Kepler's third law. Okay, so we're going to take a look at some modifications to Kepler's third law. So we're used to seeing Kepler's third law as p squared equals a cubed. But after Newton came up with his laws of motion, we can generalize these formulas to other situations. Kepler's third law really only applies to our solar system, with the sun at the center of the orbit. Newton's reformulation of Kepler's third law generalizes Kepler's third law to situations like, for example, little moons going around big planets, or planets outside of our solar system going around other stars. So let's take a look at the first equation. This version of Kepler's third law is for little objects orbiting a big object. So, for example, a little moon orbiting a big planet, or a little planet orbiting a star, something like this, where the difference in the masses is very large. So m is the mass of the bigger object in very specific units, solar masses. P is the orbital period, like we're used to from before, in Earth years. And a is the average distance between the objects in astronomical units, right, or the semi-major axis of the orbit in astronomical units. Okay, we're going to see how to apply that in a second. First, let's introduce another version of Kepler's third law. So this one is for two objects that are similar in size. So, for example, two stars in like this mutual orbit with each other. So m plus m is going to be the combined mass of the two objects, again, in solar masses. P is the orbital period in Earth years, and a, the semi-major axis of the orbit, or the average distance between the objects, same thing. And we're going to use astronomical units for a. Okay, so let's take a look at an example. This one says, a small planet orbits a star twice the mass of our sun at a distance of 3 astronomical units. How long does it take for the planet to complete an orbit? Okay, so let's start out by taking inventory of the given information. So m, okay, first of all, we should try to think about like which of these two formulas we should use. So notice it's a small planet orbiting a star. So this is a little object orbiting a big object. Stars are so much bigger than planets. So we're going to use the first version of the equation. The star has twice the mass of our sun, so we're going to write big M, the mass of the star, is 2 times the mass of our sun, so it's going to have units of 2 solar masses. We can write solar masses as m sun. Next, let's see, it orbits at a distance of 3 astronomical units, so that means that a, the average distance between the planet and the star, is going to be 3 astronomical units. And we're being asked for how long it takes for the planet to complete its orbit. That's the orbital period. So P is our question mark. Okay, and let's try plugging into the formula. So we're going to use m p squared equals a cubed, right? So this is the formula for a little object orbiting a big object. And we're going to substitute in our value. So 2 goes in for m. P we don't know, so we're going to leave it as p squared. And a is 3, so we're going to put 3 for a. And let's see, so we've got p squared is equal to 3 times 3 times 3. Right, cube means multiply 3 by itself 3 times. Okay, so 3 times 3 is 9, times 3 is 27. So we've got 27 on the side, and 2p squared on the side. And then we're trying to solve for p, so let's divide both sides of the equation by 2. P squared equals 27 over 2. And we're not interested in p squared, we're interested in p, so we have to take the square root of both sides to undo that square. So p is equal to the square root of 27 over 2. Oops, okay. P equals square root of 27 over 2. And we should plug into the calculator to see what that comes out to. 3.7. And our units are going to be Earth years. Okay, now I want you to try this one. So try this one on your own. Try to figure out which of the 2 equations you should use to solve this problem. And I'll go over the solution in a little bit. So pause the video now and try this one on your own. Okay, hopefully you tried it on your own first. So here they're talking about a binary star system. So binary star system is going to be this version of Kepler's third law. So for 2 similarly sized objects, 2 stars are going to be both roughly the similar size. It's not like a star and a planet where the star is like a much more massive object than the planet. Here the 2 stars are going to have roughly the same size. And okay, so let's try it. Orbital period of 84 years. So P is 84 years. The average distance between the stars is 32 astronomical units. So that's our A, is 32 astronomical units. And we want to know the combined mass of the stars, so we're looking for m plus m. That's our question mark. So let's write down the equation. M plus m times p squared is equal to a cubed. And we'll substitute in our value, so 84 goes in for p. We have to square that. And then a is 32 astronomical units, so 32 cubed. And let's see, we're trying to get m plus m by itself on one side, so we have to divide both sides of the equation by 84 squared. It's going to be 32 cubed divided by 84 squared. So this is the same thing as saying 32 times 32 times 32 divided by 84 times 84. And we should plug this into the calculator and see what number we get. And this comes out to 4.6. And our units here are solar masses. So we can write that as m sun. So what this means is that the two stars together are roughly like 4 or 5 times more massive than the sun is by itself. Okay, great job, success.